Now we're going to talk about something totally different, which is quantitative reasoning under incomplete information. So this is an example that you might have seen before about some famous study. And hopefully this example, tells us about a new sort of thinking paradigm on how we use information for quantitative reasoning. So let's start with this question. This description followed by question. So Steve is very shy and withdrawn, invariably helpful, but with very little interest in people or the world of reality. A meek and tidy soul. He has a need for order and structure and a passion for detail. So which one is more likely? This person being a librarian or this person being a farmer? So what do you think? Let's just try. Just tell me librarian or farmer. Yeah. Yeah. All right, so just answer the question. Librarian. All right, so some people said librarian, some people said farmer. So the thing is, when two economists ran some experiments by giving this description and asking a large number of people, most people chose librarian, and that is sort of an, a normal choice to make because of some limitation of how we think of information. And the true answer is farmer. So this is the study by Tversky and Kahneman. They won a Nobel Prize in economics for for this study, which reveals some biases that we have in judgment and how we think under uncertainty. So the next couple of slides are from this website, which explains this study very nicely. So the thing is, even if our gut feeling says that description matches with description of a librarian, that is not necessarily sufficient for us to decide librarian as the answer to the question. The thing is we need to consider the fact that there are just much more farmers compared to librarians. Just pretty much in any country, being a farmer is a much more common occupation compared to librarian. Maybe we also have our own biases because we don't work in a farm, we are at a university, so we see some librarians maybe on a regular basis, but maybe we don't see farmers on a regular basis. So maybe we also have our own biases of thinking about the stereotypical representation or characteristic of a librarian. So if we want to consider the fact that just being a farmer is much more likely, we can go with with the information on this slide. So let's just consider that for every one librarian, there are 20 farmers. So this is just based on our impression of how common these occupations are. So some of you might say for one librarian there's 30 farmers. Some of you may say 1 to 15. But I think we can agree that being farmer is just a much more common occupation. And the reasoning in here doesn't change whether we go with 1 to 20 or 1 to 15 or 1 to 60, which is apparently based on US Census, based on occupational data. The ratio is much closer to 1 to 60. So this is actually, we are being very generous about the outcome of librarian. So let's say 1 to 20. So we consider a sample of 210 people. As the ratio we consider is 1 to 20, in our sample, there are 10 librarians represented by white, and there are 200 farmers represented in green. So now we need to see for how many of these people in the sample they match the description. So the thing is that description is not just something that has 100% correlation or association with being a librarian. There could be a librarian that just has different characteristics, not being shy, not having such a obsession with structure and order, right? There could be also a farmer who has those characteristics, right? So if our gut feeling is that for a librarian, if our gut feeling is that a librarian is 40% likely to match that description, and a random farmer is 10% to match that description, then we will limit this sample to something like this. Out of those 10 librarians, now we restricted the sample to this, because out of 10 librarians, 4 of them match the description. So let's say that description has some correlation with being a librarian, so we're not disregarding that fact. But the thing is also for the population for the farmers in our sample, if that description matches with 10% of the farmers, we still get something like this. And now for deciding between those two alternatives, we can just try something like this. So probability of this, Steve being a farmer, being a librarian, given the evidence, given the description, is going to be actually 4, because 4 people in our sample match that description and are librarians, over 4 plus this, which is 20 farmers, so 4 plus 20. And the answer is, I think, something like 16%, right? Yeah, 16.7%. And the other possibility was probability of farmer given the description, and that probability would be around 87%, sorry, 83%. So the thing is, this would be 1 minus 16, which will be 83.3%. And now that we go with these numbers, although it goes against human nature, we should treat this incomplete information like this and give the answer that Steve is more likely to be a farmer, because at least based on this reasoning, being a farmer is still 5 times, something around around 4 to 5 times more likely. Any questions? All right, so but where this comes from? Well, this comes from the Bayes theorem. So here we just worked with these numbers, and we had a simple ratio of number of librarians matching the description over number of librarians and farmers matching the description, because that was the question. So for someone who matches this description, whether they are librarian or a farmer. So the fallacy here is that sometimes we consider that information determines our estimate or belief, which is which has its own limitation, because if we use this paradigm of quantitative reasoning, then we cannot rely on the information we have before receiving the evidence. So just before giving you the description, you already know that being a farmer is much more likely. So if I ask you some random person about whether some random person without any description is farmer or librarian, you would say farmer, because just being a farmer is more common. The thing is, with this thinking paradigm, we fall in the trap of this fallacy, which is information determining our belief or our estimate. So it shouldn't be like this. Instead, with a kind of a Bayesian perspective on incomplete information, the information that we receive should only update our belief. So here, the reasoning was that we consider all possibilities before receiving the evidence, right? Then the description is given to us, so we have some evidence, about characteristics of this person, and then we're going to restrict the space of possibilities, based on those like smaller parts where the evidence holds. So we restricted the space to this, and then probability of this outcome given the evidence would be the ratio, the area of this rectangle over the total area of these two rectangles. And the thing is, sometimes just our prior is about two different outcomes that are so unbalanced. Maybe we're thinking of whether some transaction is fraud or not, right? So probability of fraud is really small; it's like less than 1%. And even if we see a lot of suspicious characteristic about some transaction, that should not push us that much to say this is a fraudulent transaction. As the prior is like 1% to 99%, if that characteristic is still something that is highly, has high correlation with fraudulent transactions and low correlation with valid transactions, still the probability of that transaction being valid could be more than 50%. All right, so now let's see where, how this is connected to Bayes' theorem. Well, pretty much what we did was using Bayes' theorem without really using the formula. So with Bayes' theorem, what we have on the left is called posterior. So this is posterior, and this is prior. Sorry. This part is prior. Then this is probability of seeing the evidence if the hypothesis is true. And then this is the total probability of seeing the evidence. So the thing is, usually for the denominator, we need to kind of decompose this by conditioning it on the hypothesis. So in our graphic representation of this thinking paradigm, the posterior is here. This is what we are looking for. The prior is this. So probability of hypothesis being true in general before any evidence is presented to us is like 1 over 21. This is just because we said being a librarian compared to being a farmer, it's 1 to 20. So then the total would be 1 to 21. The goal is finding the posterior, and then we have the likelihood here. So this is the likelihood of seeing the evidence given the hypothesis being true. this tells us about, that association between the information and the outcome of interest. How much that description matches with the librarian. So for the likelihood, we assume that in the situation where the hypothesis is true, how often is it for us to see that evidence, to see that characteristic? And we also need to consider this, which is probability of seeing the evidence when the hypothesis is false, right? That would be the association of those characteristics with a farmer, right? Of course, when this part is larger and this part is smaller, then we update our belief more dramatically, right? But then the whole process is updating our beliefs. It's not totally, disregarding the prior and using the information to come up with an estimate out of nothing. So in this case, if we want to look at these percentages, I guess we get something like this. So we want a posterior. So probability of H based on those numbers. This is prior, right? So prior is just one random person being a librarian as opposed to a farmer. It was 1/21. Then the description, observing those characteristics, if someone is a librarian, that one was 40%. Then for observing the evidence, we need to break this into two possibilities, right? So here we have just the general probability that someone is a librarian times this plus the other probability, so 20/21 times 0.1, considering that there's also an association of some small association between those characteristics and a farmer. Then the result of this would be that 16.6%. This is when we went with the probabilities, but if we want to think of the numbers, well, for the numerator we had 4. Where did 4 come from? 4 was 2010 that we had in our sample at the beginning. Then only 1/21 of those were librarian, so that was 10 people, and out of 10 people, 4 were matched the description. And then in the numerator we had the same thing. So that this is the tall rectangle. Here we had the tall rectangle plus this wide rectangle, right? So for the number of people that were in this rectangle, there were 20. Where did that come from? It was the total that we had times 20/21. So that was 200 farmers to begin with in our sample, and then 10% of those 10% of those farmers match the description. And as you can see here in this fraction, 210 cancels out. So it doesn't matter, what is this sample size, because it's just about these ratios with respect to each other. But the thing is, there's actually some benefit in thinking about the numbers as opposed to probabilities, because the numbers are just more natural to our thinking compared to coming up with probabilities. And we're going to see that a bit later. So actually, the idea that you work out this equation just by saying, all right, out of 210, let's say out of 210 people, 10 are librarian, 200 are farmers. Then out of those 10 librarians, 4 of them match the description. So I get 4. But also for farmers, 10% of them match the description. That would be 20 people. So this idea of thinking of this fraction like this, there is some advantage to using this as opposed to using the probabilities. It's just more natural, and we're going to see it a bit later. Any questions so far? All right. So if you don't have questions, I have follow-up questions for you. So let's just think about a different setting. I want to see how the reasoning changes in different situations. So if we believe that farmers and librarians are equally likely to fit the description, how does that affect our estimate? Anyone? So this was the sample. The left part was librarian, right part was farmer. Now, if we believe that farmers and librarians are equally likely to fit the description, it means that the height, or this dimension of the rectangles would be equal. Therefore, what we're going to have is, the fraction would be this over this plus a wide rectangle that has the same height. And this is actually where the posterior, which is probability of hypothesis given evidence, becomes equivalent to the prior, right? So what is this ratio? The ratio is the same ratio as, this dimension is the same. The ratio would be the ratio between these two lengths. And this is the prior. So this is actually where this information does not update our belief at all, because it is about some description that matches with a farmer the same way that it matches with a librarian, right? So it is just some description that is not informative for us. Any questions? So here, the posterior equals prior. All right, another follow-up question. So if we believe that that there are equal number of farmers and librarians, meaning that these occupations are equally likely, how does that change our estimate? So let's say these occupations are equally common. How does that change our estimate? Yeah. So it changes our prior, right? So if this is the probability, total probability, then we need to split it in half, right? And this means that our prior is 50%, which is probability of the hypothesis. Then here, this is 40%. So let's say, left and right are 50%. So we can just work with a square of size 1, right? So it's 1 on this side and 1 on this side, right? So then this length is a half. This length is 0.4. For this one, this length is a half. This length is 0.1. So the posterior, which is the estimate we're looking for, would be equal to So you can see that, interestingly, this 50% now cancels out. And the result would be, well, the result would be 80%. So this is as if it is as if we don't have a prior. As if without the description, it's 50-50. So it's just a coin toss. It's just randomness. It's just total symmetry, right? So our prior, this is sort of a binary classification where the classes are equally likely before the evidence, right? So then in this case, where the prior is 50%, what happens is that our estimate is heavily impacted by the description. And this 80% is just a ratio of association between that evidence and librarian, and the association between evidence and farmer. So it's 4 to 4 plus 1. That's pretty much the equation, right? 40% over 40% plus 10%. All right, another follow-up question. So, well, what about this? What if we think that there are 20 librarians for each farmer? So it's unbalanced, but in that other direction. So then I'm going to work with a square of size 1. Each side is just 1. Now, this part, this length is 1 over 21. And of course, this part would be 20 over 21. So here in this example, the prior is already 20 over 21. And the evidence that we have is in the same direction as our belief. So then the evidence actually makes us more confident about the belief that we had before the evidence was presented to us. So this is 20 over 21, which is equal to almost 95%. Let's say, again, we have 10% of farmers matching this description and 40% of librarians. So now the posterior is going to be, well, the posterior is this area over that area plus this tiny thing here, right? So the area for this rectangle on the left is this, and then we divide it by this. And the result of this would be around 99%. So what happens here is that the evidence was in the same direction as our prior belief. So it made us even more confident in our prior belief. Any questions? All right, another question. So what happens when the joint probability of evidence and hypothesis is high? So the joint probability is probability of H and E. When this thing is large, actually the left rectangle is large. So when this value is a large value, it just means that this left rectangle, for whatever reason, just takes some considerable space. This is where the information is relevant, right? This is because we can write this as prior times evidence given the hypothesis. And we saw earlier that this part is prior, and then this part is seeing evidence given the hypothesis. And of course, the multiplication of these two numbers is nothing other than the multiplication of the two sides of this rectangle that gives us this area. So when this area is large, it means that their sides are large. So it means that the product of prior and likelihood is large. Any questions? All right. Another question for you. So this is about, I guess, a different study from the same people, Tversky and Kahneman. So some description about some individual, and then a question about which one of these two options is more likely. So Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Which one is more probable? Linda is a bank teller, or Linda is a bank teller and is active in the feminist movement. So who says option number 1? Who says option number 2? So more people select option number 2, and that's also a fallacy. This is another way that kind of our mind, plays tricks on us. So the thing is, the second probability is just some subset of the first probability. So the second one has to be smaller, but people normally select the second one as a more probable, outcome. And the thing is, in their experiment, they also, selected a different set of subjects and asked them a slightly different question. Same description, but then saying that 100 people match this description. How many of them are bank teller, and how many of them are bank teller and active in feminist movement? And that fallacy disappeared. That error in judgment disappears, because based on this version of the question, people would just, assign some larger value to the first one, maybe 8, and then smaller value to the second one, because they see that number of people for the second part would be some subset of number of people in the first part. So that's the advantage of thinking about Bayes' theorem in terms of number of people matching description compared to thinking of probability. Because probability is not natural to the way we think of these quantitative measurements and make decisions. But numbers are just more tangible, and that's one reason why it could be useful if we try to come up with explanations like this compared to updating our beliefs like this. It's the same thing, only the one on the top is based on numbers, and we can think of, all right, how many out of 10 librarians, how many of them are shy and obsessed with structure and order. It's just easier to think of these numbers compared to probabilities. All right, that was it for part 2. Any questions? Let's take another quick break, and then we move to reasoning with no information.